Yeah, hello everybody. Yes, I'm from Bluescope Steel, and the talk today would focus on one application that we have done, and that's basically debottlenecking a walking beam furnace for a hot strip mill. It's basically a reheating furnace. My name is Habib Zughbi. I am from a group called Coke and Iron Making Technology in Bluescope. We're based in Port Kembla. And the group is about 10 to 15 people. And we've got a long history of mathematical modeling, CFD, DEM, CFD, flow sheeting, other more mechanistic models, mass energy balances, and so on. And then, so Bluescope, it's basically a global solutions, building solutions company in there. We spread, we've got footprint in about 19 countries in there. We are based here in Port Kembla. It is an integrated steelworks. We've got, at the moment, one blast furnace operating. We've got coke oven, sinter plant, blast furnace, BOS, basic oxygen, steel making, casters, and painting and coating lines in there. We produce about 3.1 million tons last financial year. We probably produced a little bit more this year as well in there. Our products are mainly flat products, fencing and roofing products in there. And as I said, you know, we've got a footprint in many other countries around the world. So in Port Kembla, before we jump into this one in here, I had a few slides, but the slides were too many, so I have deleted a few slides, but we'll talk more. We have a whole range of projects basically coming from the four corners of the integrated steelworks. We've got very, very sophisticated models, such as one to simulate the hearth of a blast furnace, and that solves liquid metal flow in a porous medium, and conjugated heat transfer, natural convection, and that's really used to monitor the campaign life of a blast furnace. I mean, relining of a blast furnace would cost upward of $400 million. So we use it to really monitor the wear, if you wish, in the pad and the side walls of the blast furnace. Two other more complicated models, pneumatic transport of solids, gas solids flows in dense phase, dilute phase. And we use it across the range for design, redesign, debottlenecking, troubleshooting, and all types of different problems in there, de-dusting problems, ignition hoods problems, and there we've got a whole range of problems across the works that we apply CFD or CFD-DEM to really handle in there. So today I'm going to focus on one problem in there, and it's the debottlenecking of a walking beam furnace. A walking beam furnace is basically a reheating furnace after the slabs are made in the basic oxygen furnace, basically, and the caster in there. We take them to a reheat furnace before we start the rolling exercise in there. So they're very efficient furnaces. They save lots of money because of their efficiency in there. And we have two furnaces, such furnaces in Port Kembla. And this, the second furnace, number 2, it's pretty recently installed, 2006 furnace, but it was not operated in the most optimum way. So the plant engineers, together with us, we had a look at maybe 3 key issues in there. The first one is the quality of heating in the recuperator section. There was uneven heating, and we fixed that. And the second one, and maybe that's the major one, improving the capacity of that, and that's really focused around debottlenecking of the stack. The stack has got an induction fan and a venturi in it in there, and just by a simple adjustment in there, we really were successful in increasing the capacity by a significant amount to the tune of almost 25 tons an hour. And the third improvement, we have a better efficiency of heat recovery in there. We'll talk very briefly about each one of these 3 in there. So the walking beam furnace is pretty long one. It's about 50 meters long. The furnace proper is here, where you have two opposite basically sets of burners from either side in there. And the slabs travel counter current in that. So gas go this way and the slabs go this way in here. So after the furnace proper, these hot gases keep on flowing, heating the slabs in there. And they started to go through a very convoluted, basically. In here, they make a very 90-degree band in there. They go up, they make another 90 degrees band until they get there, and then they drop into that recuperator section in there. So it's pretty convoluted geometry, pretty big geometry in there. And okay, so the first one, the cold air, I should mention that it is basically injected right at the moment. That's where it shows in there, right in here. So the hot gases come in here to control the temperature of the hot gases. We inject a fair amount of cold air in there. So in here, in the recuperator section, you've got about 12 bundles of vertical tubes in there that used to really recover some of the waste heat in there. And what was noticed in there, that there is really uneven heating in there. The difference was something like between 100 and 150 degrees difference across the width of the recuperator in there. So the only thing was that the hot gases from the furnace were well mixed. The only thing was how well the cold air was mixing with the hot gases in there. So we started to look where best to inject the gases in there. So we moved it from here right to here. You cannot really see it from here, but it's a very, very swirly type of flow. And by injecting the air right in there before it drops into the recuperator, did not have the time or the space to mix. So it was coming in and then staying on one side, and therefore resulting in this temperature profile. Just simply by moving them to here, where it's got a lot more time and space to really mix in there, we sort of moved from this profile to about this profile in there, which resulted in a much, much reduced non-uniformity in the heating in the recuperator. Okay, the change has been implemented, and the results were achieved basically in there. So the second one is basically how can we improve the capacity? Because we have two furnaces in there, and the gas balance in an integrated steelworks is always a challenge, because we've got indigenous fuels. We've got a blast furnace gas and coke oven gas that we used as fuels in there. And if we have good balance, we can save millions of dollars on natural gas purchase basically in there. And sometimes we have to run the two furnaces, and that really stuffs up the balance of the gaseous fuels across the plant in there. So we were trying to really improve the capacity so that we can really run one furnace rather than two in there. So the engineers came to us in there, as you have seen that venturi in the stack, and said, what can we do in there to really improve the capacity in there? Okay, and their focus, can we really obtain a more negative pressure at the bottom of the stack so we can push more gas in, we can heat more slabs basically in there. Okay, so this is the stack, there's the venturi, there's the gas from the recuperator, and the nozzle from the induction fan comes in here, opposite to it in there. And maybe there are 5 factors in there that will control the performance of the venturi in there. There is the throat, the straight section between the converging and diverging section, length and diameter in there, the gas flow rate, and the position of the nozzle itself. So very briefly, we tested all the other 4. We found virtually no results, no improvement in the results. And then we focused on one item, and this is where does the inlet from the induction fan hit the venturi in there. And that's where really we achieved the results in there. And that's what I mean in here. Right, the old one, that's the venturi. That's the converging section, straight section. That's the throat. And that's the diverging section. It was coming right in here at the bottom of the straight section in there. So we did some parametric runs and up, down to here, further down, and so on. And what we found is just by this simple and cheap, basically, change, if we really shift it from here to there, then the whole function of the venturi changed significantly in there. These are the pressure contours and a little bit more theory. There's nothing new about the theory, I must say. There are papers from 1945, well before CFD, talking about Venturi functions, and they actually talked about where is it best to really put the motive fluid in there. So just by looking at that, the theory behind it is that when you hit that straight function, this whole thing should have been really totally well mixed basically in there. And as you can see, if you do it in here, this thing keeps on mixing it almost to the end of that straight section. By moving it down to here, it's almost did what it really supposed to do in here, and we got a much better mixing in there. And therefore, as you can see in here, with the pressure contours in there, this is a lot lower pressure than it was basically achieved in there. So this is where it is in here. It's about there. By moving it down to here, we were further down, about 300 pascals. They're 300 pascals lower than what it was before in there. So the engineers were convinced basically in there, and then they went and they did the small change in there. It's not really a big change in there, and it was implemented, and indeed the capacity, as I said, has gone up by about 25 tons per hour, and there was a significant savings per ton, so that really added up to about $1 million, only that single one per year without the first one in there. One last improvement, after the furnace proper, the hot gases keep on flowing and the slabs countercurrently flow in there. The furnace is about 1.8 meters high, so there were no obstructions for the gas to be redirected to the slabs. So the gas was really flowing in there and making some contact with the slabs in there. The efficiency of heat recovery was not really as good as it can be. We've got a second furnace, actually. It's got something in it in there. So we did the basic flow and heat transfer runs in there. We installed, we call it a plate, but it's really a huge hemispherical structure in there to force the gas more towards the slabs in there. And as you can see, we achieved basically a lot better heat temperature distribution compared to this one in there. These are the higher temperatures were really spread a lot further away, and then the temperature of the exit flue gases were significantly lower than before in there. So to summarize, basically we used, that's not the most complex of our models by any long shot. You know, it's a simple fluid flow and heat transfer. However, we're lucky to really pick on 2 or 3 applications for one particular equipment in there, where each one was pretty successful in there, and the result was very, very satisfactory. Thank you.